Now, how do we evaluate the cost of the sort merge join? Well, we are going to sort R, sort S, and then we will scan R and S and merge them in memory. So the cost is basically the cost of sorting R plus the cost of sorting S plus the cost of scanning R and S. In the worst case, actually, all of the joint values of R and all of the joint values of S are exactly the same. In that case, the output is the cross product of all the tuples in R and S because everything matches. So in that case, it degenerates into a nested loop join with cost of vertical bar R times bracket S, which is actually lower than the cost of the sort merge join. But that's extremely unlikely, and it's the kind of thing that a good optimizer would keep an eye out for and avoid. So we can usually assume that in a sort merge join, there's plenty of distinct values in the join columns, and those little mini cross products where we take multiple join keys on R multiplied to the same join key on S, and we form all pairs, that only happens on a handful of tuples, like we saw in our example. Assuming that's the case, and we don't pay extra IOs for those little mini cross products of duplicates, how big does the buffer have to be to do this in 2 passes each? Well, suppose that the buffer is bigger than the square root of the larger of R and S. So then both R and S can be sorted in 2 passes, and given that, we can now compute the cost of our algorithm on our inputs. R is 1,000 pages, and we know that sorting is 2 passes of R, so that's 2 read and write passes, so that's 4 times 1,000. Sorting S again takes 2 read and write passes, so that's 4 times 500, and then the final pass to read R, read S, and merge them together in a streaming fashion, and that's 1,000 plus 500, for a total of 7,500 IOs for this sort merge join. Now, in general, figuring out the cost of the sorting the output of the join is a bit tricky because we don't know how big the output of the join will be. It depends on how many matches we find between these 2 tables, but in this particular example, we happen to know that every reservation has exactly 1 sailor. And so the output is going to be exactly the same number of rows as the input table R, the number of reserves tuples. So we can estimate the cost of sorting the output here as the cost of sorting R, which you can see below, and that's something like 4,000 IOs for a grand total with block nested loops join of 9,500 IOs to do the join and sort the output. Compare that to the cost of the sort merge join, for example. In the sort merge join, we sort R, we sort S, and then we scan the 2. As we said, that's 7,500 IOs, which is cheaper than the previous slide. So in this case, we can combine the join using sort merge join, then we get the order by for free because the output is already sorted, and we do it more cheaply than doing a block nested loops join and then sorting its output. Now I want to show you an important refinement to sort merge join that can save some more IOs. This is something you probably want to do every time you think about sort merge join, so keep this in mind. This refinement is essentially going to take the joining path of sort merge join, so that second phase of sort merge join, and combining it into the last pass of merging during the sorting algorithm that we already learned. So our good old external sort algorithm that we learned before is going to have an extra little wrinkle here when we do joining in this last merge pass. Let me show you how this works. To do this, we need to have enough buffers in memory to store all one page from each run of S and R on the second to last pass of sorting. Here's how it goes. In pass 0 of R, we are going to read R and write out the sorted runs to the disk as usual. For pass 0 of S, we are going to read S and write out to the disk as usual as well. Now, in the final merging pass of R and S, let's say it's pass 1, we are going to merge the R runs and the S runs in memory. But at the same time, we are also going to look for pairs across R and S for joint matches. So while we are merging the R runs, we always know the minimum value of R in memory. At the same time, at any given time while we are merging the S runs, we also know the minimum value of S. So we can do these next calls that we did in the merge join algorithm as those runs are being merged. So in essence, if we go back to the join algorithm for sort merge join, whenever it says next, imagine doing that next on the merges of the final merge of R and the final merge of S in each of their sort algorithms. In doing this, we are going to avoid writing out the final pass of R and the final pass of S during sorting. So we are going to lose one pass of R and lose one pass of S. The cost now becomes 3 passes of R plus 3 passes of S total. That's in this case going to be 3,000 plus 1,500, which is only 4,500. But in this case, however, we need to have at least one page from each of the runs right before R and S are fully sorted in memory, as otherwise we won't know which run to read next from during the merge phase. In other words, we need the number of runs in the last merge pass for R and S to be at most b minus 1.